Good evening. And welcome to our third lecture in our spring series here. A very exciting topic, exoplanets. Really the hottest field in astronomy, I think one could argue. It's a field that, when I was in graduate school, people were talking about looking at planets around other stars in the early 90s, and we thought they were crazy. Including one of my office mates is Paul Butler, who's now a Carnegie astronomer in our sister department, the Department of Terrestrial Magnetism in Washington, D.C. And Paul was one of the first to then develop this technique that is being used now to find many, many planets, which you'll hear about tonight. Speaking of the Department of Terrestrial Magnetism, they don't do terrestrial magnetism at all anymore. They probably should have changed their name. What they do a lot of now is they do planetary science around other planets for the most part. And so they have a part of their department involves some astronomy. So we actually have at Carnegie Astronomy, we have many of us here in Pasadena, and then we have the folks who work kind of on planetary systems, planetary disks and things of that sort in Washington, D.C. But we consider ourselves one big happy family. And so a few years ago, we decided that it would make sense for the two departments to do more work together. Even though we're separated by 3,000 miles, we have technology and the capability to do that. And we are particularly here in Pasadena, where we tend to work on large-scale questions, cosmology, and galaxy evolution, and things like that. We thought it would be really great for us to know more about the planetary work going on in our sister department. So we created a new postdoctoral fellowship called the Origin Fellow. And this is a fellowship that involves the candidate spending 2 years in Washington, D.C. at that department, and then 2 years here in Pasadena. And so tonight's speaker, Johanna Teske, was the very first Origins Fellow. And I could say we could not have made a better choice. She's been truly amazing and wonderful, and particularly about helping to bridge the two departments together. And you'll see Johanna's work here involves both understanding planets, but also understanding stars and that connection. And that's a connection that really helped the two departments. Those are areas we kind of both focus on. And I'm particularly proud of Johanna because well, like all of our fellows, they go on to do bigger and better things, and she just has been awarded a Hubble Fellowship, which is really the most prestigious fellowship one can get in astronomy, so, which means she gets to stay at Carnegie, this time for a longer period using this Hubble Fellowship. So let's congratulate her before her talk on this, because it's a really great accomplishment for her. And so we're happy that we get to have her at around Carnegie for a while longer. Anyhow, with that, let me introduce tonight's speaker, and we'll have Johanna Teske tell us all about exoplanets. Johanna, come on up.
All right, thanks very much for that very nice introduction. Like John said, my name's Johanna, and I'm the Carnegie Origins Postdoctoral Fellow, now based here in Pasadena. I'm going to talk tonight about exoplanet genetics, which you might be wondering what that means, and I'll get to that in a moment, but I wanted to first start with the question that I always get asked when I'm talking about my job and how I've gotten here, and that's, like, why are you an astronomer? What made you go into astronomy? And so it's a little bit hard to see here, but this is a still shot from the movie Contact, which some of you may have seen before. This is Jodie Foster starring in it as Ellie Arroway. And this was a movie based on a book by Carl Sagan by the same name, based loosely on the life of Jill Tarter, who I got to meet a few years ago, and that was amazing. But Ellie Arroway in this movie is trying to search for life on other planets. And when I first saw this movie, I think it came out in the 1993, 1994 area, I was enamored with it, and particularly this quote, which she says to one of her friends while they're sitting outside looking at the stars one evening, which is, there are 400 billion stars out there just in our galaxy alone. If only one out of 1 million of those has planets, and just one out of 1 million of those has life, and just one of 1 million of those has intelligent life, there would literally be millions of civilizations out there. And so I heard that as a 8 or 9-year-old and was hooked. That's pretty much when I know what I wanted to do. Ellie Arroway uses radio telescopes for her search for extraterrestrial life. I am more used to using optical and infrared instruments on the telescopes here, pictured at Las Campanas Observatory. So this is what my observing view looks like. It's not quite the Grand Canyon, but it's still quite beautiful. So now, on to the title of my talk, Exoplanet Genetics. The first word, exoplanet. What is an exoplanet? Exo, you think of outside, exoskeleton, planet. I think most of us are familiar with what that means. Bodies orbiting the sun in our solar system. So exoplanets are planets outside of our solar system, planets that don't orbit the sun. Almost all of them that we know about orbit other stars, although there seems to be a hint of a population of rogue planets that don't necessarily orbit stars that might have been ejected from other solar systems. And so it's not known whether these planets were formed as their own or outside the star system. Here is a picture of an artist's rendition of what all these different exoplanetary systems would look like. But that's just an artist's rendition. The picture in the right is a little animation of real planets. This is via a technique called the direct imaging technique, which I won't talk about that much tonight, but I wanted to give you an idea of that, what real planets look like. We're able to take pictures of some of the youngest and most giant exoplanets right now around their stars, and this is the kind of work that's being done at the Magellan telescopes right now. So that's the exoplanet part. What about the genetics part? So I was chatting with some of my colleagues at a teaching workshop, some people who work in biology, and they were like, exoplanet genetics, that does not make sense. Like, you don't know what you're talking about. And so I came up with this diagram. I found this in one of the genetics journals, and it illustrates how we learn basically about humans. There's the physiology, individuals' behavior, also the environment where they grow up, and then obviously genetics, what they inherit from their parents and previous generations, and that all feeds into everyone's development. And so I can modify this to how do we learn about exoplanets? And so instead of physiology, for humans, we have circulation and convection and different types of heating and cooling, both within the interior of exoplanets and in their atmospheres. For environment, just like we can be influenced by our peers or our siblings, exoplanets can be influenced by other planets or other stars that are coming by their star out in space. They can also migrate inwards towards their star and away. They can be scattered, like I referenced, outside of the solar system. And we even know of some planets that seem to be experiencing evaporation. Their atmospheres are evaporating because they're so close to their stars. What I'm going to focus on this evening is this genetics part, which is what we think planets somehow inherit from their host stars, perhaps through the disks of gas and dust around the star that they form out of. And all of these things feed into really my main driving interest, as you gathered from the first slide, which is finding life on other planets. So first, to learn about exoplanets, we have to find them. That's good to have something to study. So briefly, I'll go over the two main techniques right now for finding exoplanets. There are a few other ones, but for the purposes of this talk, I'll just focus on these two. So the first one is the transit method. And this is when a planet is passing, between us and the star, and we can tell, if you're looking at the bottom plots, this is the light coming from the star versus time, and the planets block out a little bit of that light as they pass in front of the star. This is the type of technique that the Kepler space mission used to discover thousands of exoplanets in our galaxy. You'll notice that the bigger planet causes a bigger dip than the smaller planet. That's important to know for the next slide. And you'll notice that it's going in front of the star, and so blocking out some of the area of the star. And so this technique lets us measure the radius of the planet relative to the host star. I mentioned briefly that I was just at a teaching workshop. I am very interested in education and outreach, and so I'm gonna do a little bit of that here. And so I want to pose a question to you, which you can think about for a moment. You see this system from above of a multi-planet transiting system. And so on the previous slide, you saw the light curves, which were just the amount of light coming from the star as a function of time. And I want you to predict, either on a piece of paper or in your mind, what you think this multi transiting planet light curve will look like. And you notice that there are some planets of different sizes, and that they might both be in front of the star at the same time. So take just a moment and think about that. Have a picture in your mind of what the light curve would look like. Okay, so now I'll give you the answer. I have to say I modified this a little bit by hand because I don't think it was showing a correct depiction, but I think you'll get the idea. So it's going to zoom in to the transiting view so that we can see the planets in our plane of sight. And the first planet goes in front. It's the biggest one that causes the biggest dip. And so now it's not off on the face of the star. The next two planets are coming, coming, coming. There's one, there's two, there's a part I made, and then they finish crossing the star. So this is the type of technique that we've used to detect many, many small multi-planet systems, so systems that have a lot of small planets in them. Kepler has found hundreds of these. So that's the transiting technique, blocking out flux from the star, or light from the star. The second main technique is called the radial velocity method, or the Doppler wobble method. And so this is showing that as a planet orbits the star, there's a small little gravitational tug that the planet has on the star. So normally we just think of planets orbiting stars, but the star is also making its own little circle around their common center of mass. And as that happens, when the star moves away from us, its light is redshifted, which is shown in the diagram, just slightly. And when it's moving towards us, its light is blue shifted, just like when you hear an ambulance going by and the frequency of the sound that you hear changes depending on whether it's moving towards or away from you. This technique gives us a measure of the relative mass of the planet. So transiting technique gives you the radius, and this gives us the mass because we have to, via this technique, we can understand how much mass is needed to cause that pull on the star. I wanted to give you a little bit of a spectroscopy snapshot, and this will become clear on the next slide. The instrumentation that we use to detect planets with the radial velocity method, they're called spectrometers. And so very briefly, I just wanted to introduce you to a basic spectrometer. And so in all of these panels, you have a light source, which I'll explain in a moment. Then there's a slit, which is controlling basically what you're looking at on the sky. So instead of just letting in all of the light, you're focusing on one star, one galaxy, or part of a galaxy. And it also controls how big the image is on the detector, so how finely you're sampling the light. The next part is the dispersion. So a lot of people think of that as like a prism. It's breaking up the light into its different color components. And then the parts on the right are just what would be on the detector of the spectrograph. And what this technique allows us to do is measure the different jumps of electrons in atoms, and so tells us what types of energies are exciting those electrons in the atoms, and thus what kind of medium they're in, the environment. So the top is what we call a continuous spectrum, and that's just if you have a hot, dense ball of gas or something solid and it's emitting light. The second one is what we call an emission spectrum. And so an example of that is, you may have seen in your chemistry or physics classes when you have a tube of ionized gas and it's lit up and is glowing bright, kind of like neon lights, that causes an emission spectrum, which we can observe. And then the last panel is really what we see when we observe stars, which is a light source, which you could kind of think of as the interior of the star. And the star is surrounded by a cooler atmosphere, which is represented by that cold gas. And so as the light passes through the cold gas, or the stellar atmosphere is absorbing some of the light. And so that's what those black bars are. That represents what's being absorbed by the star. And so this is important because in the radial velocity technique, we're not just measuring sort of the wiggle of the sine wave of light, but we're looking at, how the spectral lines shift back and forth with the motion of the star. And these shifts are greatly exaggerated in this graphic. Really, it's fractions of a pixel on the detector. And so it really requires both very precise reduction techniques and analysis of the data, but also very high quality instrumentation. And that's one of the benefits of being at Carnegie. We have world-class instrumentation and a world-class telescope. And so that leads me to this slide, which is the Planet Finder team at Carnegie. I'm there as well as some of our staff scientists, and Matthias Diaz is a graduate student in Chile who's working on his PhD, and Jennifer Burt and Sharon Wang are also postdocs. And so we all work together in this planet finding campaign at Carnegie using, what else? The Planet Finder spectrograph. So this is this is a picture of the instrument bolted onto the telescope. I have a couple of the different parts labeled there, like the slit, the equivalent of our prism, our disperser, where the optics are, where the camera is. But I just wanted to give you an idea of what a real spectroscope looks like. You can see in the corner there the size of it. It's very large. This is a picture of one of the staff scientists, Jeff Crane and I, filling the coolant in the instrument to keep it at a stable temperature. And it's all insulated to keep it very stable throughout our observing, so that any changes in the data we know are due to the star and not the instrument. And just briefly, I wanted to plug, we had an exciting paper that came out last year. One of the benefits of working at Carnegie is that this planet search survey has been running for 7 years now. And so that enables us to be able to detect relatively long period planets that are far away from their star, versus many of the transiting exoplanets that have been detected, which are pretty close in. And so we detected these 3 planets around these twin binary stars. So the stars orbit each other, and one of them has 2 planets that orbits it, and the other has 1 planet. So that was a fun press release to write. I'm a Star Wars fan. So we talked about my title, and then how do you find an exoplanet. So now really digging into the content of the talk, what is interesting about exoplanet genetics, and what do I mean by that in terms of my own research. And so I want to understand exoplanet diversity, definitely with a lens towards Earth-like planets, but also just what's out there, what is possible to be formed around different types of stars. And I'm going to focus in particularly on how exoplanet composition informs us about how Earth-like planets are. Here I have sort of a pictorial diagram showing the concept of whole planet coupling, and how the composition of the exoplanet and how that relates to plate tectonics is influenced by the weathering from climate and the atmosphere, so the weathering of rocks on the surface of the planet, plate tectonics and motion underneath the crust of our planet also releases gases, and so that feeds back into the atmosphere. The tectonics of the planet also influence how much of a magnetic field we can have due to the internal heating of the core of the planet. And then if there's a magnetic field or not, and the strength of that then controls how much of an atmosphere we can have and for how long. And so actually, instead of habitability, I like to think of it as Earth-likeness, because we know that Earth is habitable, but in terms of habitability on other planets, that's hard to characterize at this point. And so I'm interested in measuring exoplanet composition as is related to how Earth-like the planets are. So the 2 exoplanet detection techniques that I talked about, the transit technique and the radial velocity method, that gives you the radius and the mass of the planet. And that enables you to measure the density, or the bulk density of the planet. And that is related to, luckily, the composition. And so on this graph, I have on the x-axis the mass of the planet. This is a smattering of some of the most recent discoveries from various missions. And the coloring corresponds to what instruments on the ground were used to follow them up. So x-axis is mass, y-axis is planetary radius. And then in addition to the colored points, you see these colored curves. And those represent different bulk compositions of planets. You can see Venus and Earth down there in the corner. And by measuring both radius and mass, we can start to place planets on this diagram and see how similar at least their bulk composition is to Earth or not. But this is pretty challenging. Not only do we need to have a space mission, to really get the small planet radii with the transiting technique, but measuring the masses of these planets with the radial velocity method is actually quite challenging. And so here I'm showing the planet mass again on the x-axis, but now the y-axis is the number of observations that was required to make that measurement of the planet mass. The color coding is the orbital period, and you see that as you get to smaller planet masses, and these are in Earth masses, so Earth is on the axis over there, the number of observations just goes up. I have in a box the Proxima Cen B planet, which is the smallest radial velocity detected planet thus far. I have X'd out Alpha Cen B. We thought there was a planet around that star, but now we think it's probably just due to the star's activity. But the takeaway from this is getting those mass and radius measurements is actually quite challenging. And so even getting a bulk density for a large number of exoplanets is hard. And so that's where this exoplanet genetics idea comes in, because we think that there are connections between the compositions of stars and the compositions of their planets. And the compositions of stars, at least right now, are much easier to measure than those of exoplanets, at least directly. So that's why I'm studying stars. I'll get into that more in a moment. The last two speakers were both theorists, and that's probably also how the last speaker will frame her talk. So I wanted to give you an idea of what an observer's environment looks like. So this is me at the telescope at Magellan in Las Campanas. And so you can see both the instrument control panel, so that's where I'm controlling the spectroscope. I have a quick data reduction, making sure the data quality is what I want, and that I'm getting the range of wavelengths that I want in the data. I have then on another computer the full data reduction going, so that will give me the scientific quality data that I need to be able to analyze the stars. Also very key, monitoring the weather. I was just there recently and we had a few nights closed due to high wind or high humidity, so that's also always important for observers. You can't control the weather, unfortunately. And then my observing log, where some people do it electronically, I still like to keep written notes of what I'm observing, and then my research notebook, which I carry with me at all times. So that's what it looks like to collect data or spectra on the exoplanet host stars. What have we learned from this data? Well, we know that giant planets, like the size of Jupiter or a little bit smaller, prefer to form around metal-rich stars. And when I say metal, that can mean different things to different people. For astronomers, that usually just means anything that is heavier than hydrogen and helium. So that's a lot of stuff. In this plot, it's parameterized as the iron abundance in this star. And so it's the iron abundance relative to the hydrogen abundance, which is what stars are mostly made of. And then the little bracket notation means relative to the sun. And so 0 on this plot is the solar iron abundance. And you can see on the y-axis is the relative frequency, and I have plotted different populations of stars. So in the dashed red line is stars that host giant planets, and you can see that that distribution is skewed more towards the larger values of the iron abundance. In blue, a solid blue line is the super Earth and Neptune hosts. So super Earth, what is that? That's a planet that's in between the size of Earth and Neptune or Saturn. We think this is the most common type of exoplanet out there that we've discovered so far. And there's nothing like it in our solar system, at least not that that's confirmed. So that's interesting. But you can see that that distribution isn't as skewed towards the higher iron abundances. And then the black dotted line is stars without planets. I have without in quotes because that probably just means the planets haven't been detected around those stars yet. This was from a survey in 2012, but the result still holds that giant planets form around more metal-rich stars. So this makes sense in the context of planet formation because we think that these disks of gas and dust from which planets form, when they have a higher content of heavy elements like iron, that they have a higher rate of smashing together of grains and what we call planetesimals, so that they can form the roughly 10 Earth mass cores of giant planets fast enough when there's still gas around in the disk, so that then the giant planet can accrete its large gas envelope and become a gas giant. And that seems to be very much tied to these initial conditions in the disk around the star, and thus we think the star. So another make a prediction moment. I hope it's not too obvious, but what do you think? Will small planets show a trend with the amount of metals in their host star or not? So think about it for a moment. Okay. And the answer is small planets don't seem to care much about their host star metals. And I'll walk you through these graphs. Both of them are based on the Kepler data. And so Kepler really is this treasure trove of small planets, although most of them are at relatively short distances from their stars. The plot on the left is showing the relative planet occurrence rate for stars with a iron fraction greater than the sun versus less than the sun. And you can see that for those gas giant planets, there's definitely a jump in the occurrence for the higher metallicity stars, we call it metallicity. And then it drops pretty quickly for these gas dwarf super-Earth planets and the terrestrial rocky Earth-like planets. But the dashed line is a 1-to-1 ratio. So this paper suggests that there is still some preference for small planets to be around more metal-rich stars, if it's definitely not as high as for the gas giant planets. The other plot is showing the distribution of stars known to host small planets in the red histogram versus stars not known to host small planets. And because they're setting a limitation on how far away the planet is from the host star, they can say, we've looked, and if there was something there, we would have seen it. So we know that these stars don't have small planets in this orbital period range. And they find that this metallicity, they're parameterizing it as just a bulk M, many metals, so not just iron. They say that they're the same for both populations. So there's still this debate about whether small planets require more metals than stars that don't host small planets. But all this is really based on iron or a few elements, and there's many more elements that we know form in stars, as you probably heard about from Tony in the first lecture. And so this is our traditional periodic table of elements. There are many more than just iron. I liked this graphic. This is the periodic table of Earth, the abundances in Earth's crust by weight. And so you can see there are definitely some dominant elements in Earth, but that there's this wide range that we have yet really to explore in small planet host stars. And so that's what I'm interested in. Why would we think that observing the star would tell us something about the planet? We know there's this connection from the giant planets that it has something to do with their formation and needing to form those cores fast enough. But what about the small planets? Well, in our solar system, we see this correlation, and it's a little bit hard to read, but these are just different elements, the red dots. And there's a correlation between the planet building blocks, so primitive material in our solar system, what's called chondrites, and the sun's composition. And it's not a perfect correlation. There are some elements that don't correlate very well due to different processes in the star or different processes in the primitive material. But for most elements, there's a pretty good correlation. And so this gives us hope that by observing something in a star, the composition of the star, we can learn something about the composition of the small rocky planets, or at least the material that went into forming them. We also know that when modeling the Earth's composition, particularly the size of its core or the composition of the Earth's mantle, that including the sun's composition in those models as some of the starting ingredients, or a prior, if you will, doing that produces a more accurate model of the Earth. You get back closer to the values that we know are true for the Earth in terms of the core size and these composition parameters. And so both that we see the primitive material being similar to the sun and that we can better reproduce the Earth's composition by including information from our sun suggests, again, that the star composition matters in determining the composition of small planets. So, if we take this as an assumption, we think that the host star composition is somehow related to small planet composition. If we don't know exactly how, what can we do with this information? So I'll highlight what we're doing now, which is assuming that this relationship exists, and assuming that the ratios of different elements in the star would match those in the planet, and making some best guesses and predictions about small planet compositions and also their properties. And then I'll talk about in the future how we might test these relationships with more observations and experiments. So right now, I love this. We're going from star to stone, and it's actually based on a book that has the reverse title, Stone to Star. By using, if we assume the top relationship that the sun's composition is related to the Earth, as I talked about before, then we can take a different stellar composition and using a similar model as we did to reproduce the Earth, try to reproduce what the composition of the small planets would be around that star. This involves calculations not done by myself, but by my collaborators that take an initial composition of gas and dust and condense that to form the rocky bodies. The simulations can then follow that rocky body through its evolution when it's cooling and differentiating into the core and the mantle and the crust and tracing the different mineral phases that go into each of those. And then also seeing how then the fully differentiated planet evolves over time, and particularly how radioactive sources of heating would contribute to plate tectonics or not. Which we saw from one of the previous slides, we think is important for a planet being Earth-like. It was quite nice. I had a press release earlier this year working with collaborators at Ohio State University as well as Arizona State University. When we took two known small planet hosts, Kepler 102 and Kepler 407, with their host stars. The host stars of these planets have different ratios of magnesium to silicon in the star. The sun is about 1, and we chose one star that was a little bit higher and one star that was a little bit lower. And using those different starting ingredients, we tried to predict what the interiors of the small planets would look like. And you can see that the one on the left, which is Kepler 102b, it is more magnesium rich, and so there are compounds like olivine and garnet and ringwinite that we think might make up that planet's crust and mantle, versus the other planet, Kepler 407b, which is more garnet rich. And so we think actually that garnet would be a less flexible mineral. And so in terms of the probability of plate tectonics, just by following through the composition of these planets based on their stars, the one on the right would be less likely to have vigorous plate tectonics and thus maybe less Earth-like. So those are the kind of predictions we're able to make right now, which is pretty cool. Moving forward, we're hoping to predict planet masses and radii based on just having the mass or just having the radius, and then be able to test those with observations like I talked about before. Both now and in the future, there's also this experimental side, which I think is really cool. I'm an astronomer, so my experiments or my data collection is really at the telescope, which I love. It's my favorite part of my job. But I really, in high school, liked chemistry, and so getting back to doing some experiments in the lab has been quite fun. Here I'm showing an undergraduate student that I worked with from the University of Maryland, and that's her, Janelli. And then Janelli and Colin, who's a postdoc at one of the other Carnegie departments, the geophysical lab. And so we were doing high pressure, high temperature experiments using little capsules of material that had different ratios of the magnesium to silicon, and squishing it and putting it under really high pressure and high temperature to see how that type of material would behave in conditions that mimic the interior of a rocky planet. And so we're still working on these experiments and getting the results published, but I just wanted to give you an idea of what the data look like for these types of experiments. These are data sort of slices through the final product of that material being squished and compressed and exposed to very high temperature. And so this is what the magnesium content of that little sample looks like, the aluminum content, and the calcium content. And we actually found an unexpected compound in the calcium content called monticellite, which, again, we're sort of still trying to figure out what that means, especially in this context of plate tectonics and interior dynamics in the planets. But we're really hoping to do more of these types of experiments and continue the collaboration between Carnegie departments. So, talked about what we're doing currently. So what's next for Exoplanet Genetics? As I alluded to, so far, all of the studies of elements beyond iron in small planet host stars, so stars that host small planets, and small stars that host small planets. All of those have been comprised of relatively small samples, and this is in large part due to the faintness of many small planet host stars. The Kepler mission was staring at one patch of the sky and just monitoring all the stars in that part of the sky, but didn't have any sort of preference for which stars it was finding planets around. And so many of them are very faint. And so it's hard to follow those up, both for measuring the masses of the planets with the radial velocity technique and for getting the stellar abundances, particularly elements like carbon and oxygen. Their spectral features are weak, and so you need very high quality data to do that. It's hard to do that with faint stars. And so how do we solve this? How do we find, or how do we get a population of small planets around not faint stars? And it might be obvious to people who are fans of astronomy, but the answer is looking for planets around closer by stars, stars that aren't so faint. Stars that are closer to us are going to be brighter, just because the distance that the light has to travel isn't as far. And so the next big thing that's coming in terms of exoplanets is called the Transiting Exoplanet Survey Satellite, or TESS. And the idea behind TESS is to survey the entire sky to look for these transiting exoplanets. It's expected to find something like 1,200 new exoplanets, all within a small radius around the sun, and so very close by. And something like 450 of those are predicted to be Earth-sized planets, so between 1 to 2 Earth radii. So this little animation will zoom out from the sun and show you planets that weren't detected by Kepler, just other planets. That's the gray ones. In purple are planets that were detected by the Kepler mission. You'll see it's just this cone right out towards a specific area in the sky. And then the orange points are those planets that are predicted to be discovered by TESS. And pay attention because they start out quickly because we're starting right in close. So right here, already 3 parsecs is something like 9 light years. And so moving outwards, look at this like chicken pox of planets that we're supposed to find. There are some Kepler planets coming out, but all these TESS planets are going to be right in close to us. And that's exciting for the radial velocity method, that's exciting for the host star composition, and for future studies of exoplanets when we're trying to do direct imaging of smaller planets or not as young planets. It's very important that they're close by. That makes it possible to do more detailed studies of their atmospheres and compositions. So with this mission, what am I going to do with this? What's Carnegie going to do with this? So, turn that sound off. In the upper left, you'll see a little movie of us working on PFS. It's open in this movie. Usually it's not. It's closed up and sealed. So this is sort of a rare inside look. We were doing maintenance on it last year. And then you'll see the reminder of the radial velocity technique. And the idea is using the Planet Finder spectrograph to follow up on many of these TESS targets. TESS will measure their radii, and we want to know their masses so that we can get that bulk density measurement. The plot on the bottom shows planet radius on the x-axis versus the orbital period in days, so how long the planet takes to go around the star. And the gray points are everything that's predicted to be found by TESS. And the pink points are those planets that TESS will be able to observe, or those stars that TESS will be able to observe the longest. And so that's where it will be able to look for the longest period planets. Because TESS is an all-sky mission, it's really only taking short chunks across the entire sky, but those chunks, as you'll see in a video in a moment, overlap at the poles. So when those are overlapping, TESS has more coverage, more time coverage, and is able to find longer period planets. We're interested in the longer period planets because we want to find things that could be in the habitable zone, have liquid water on the surface, and those have to be at just the right distance away from their star, not too close. So we're hoping to use PFS and the radial velocity technique to follow up many of these TESS planets. We're also hoping, with another Carnegie resource, to really dive into a new regime of exoplanet studies, we think that many small planets form around small stars. And so on the plot on the top, I have the mass of the star now on the x-axis in solar masses. So 1 is the sun, 10 to the 0. And then on the y-axis, I have the planet mass. And you can tell that as we go to smaller planet masses, the stellar mass, the host star mass, also generally goes down. And so we know that smaller planets tend to form around smaller stars, and that smaller stars are cooler, and so they emit more of their radiation in the infrared at redder wavelengths. And so it's better to go to the infrared and use infrared spectroscopes to study these stars. Carnegie is a relatively new partner in the Sloan Digital Sky Survey, SDSS, and we're very excited that there's a new instrument on one of our smaller telescopes at Las Campanas Observatory called Apogee. It's Apogee 2, actually, and it's an infrared instrument, spectroscope, that is capable of observing many stars at once. And so the thought is that we can use this instrument not necessarily to detect the planets around the small stars, but to study the stars themselves and measure the compositions of those stars, which really no one has done before. There aren't a lot of very precise, detailed ways to measure the composition of small red dwarf stars. Some of my collaborators are really pioneering that at this moment, and so Apogee is the perfect instrument to be able to do that. And so soon we'll be able to have the radius and the mass and then the composition of the stars, and we can put it all together and hopefully learn and learn about the exoplanet diversity from the TESS mission. And so I started my presentation with a reference to a movie, and I think it's very serendipitous. I'm giving this talk so close to Hollywood. And so I'll end with what is to me a pretty awesome movie preview of what's to come with the TESS mission. And so now I'll turn on my sound. And this is an animation, but I think it very aptly shows the capabilities of TESS and what's to come.
This is the search for exoplanets. This is TESS.
You want to go see that movie, right? Okay, so that's not science fiction. That's really what's coming, and that's part of the reason I'm so excited about this new mission. So takeaways from this talk, wrapping up, talks about what exoplanets are. They're planets that don't orbit our sun. There might be some of these rogue exoplanets. Most of them probably orbit stars. And I don't think I mentioned this, but we know of something like 3,500 of them at this point, and there are many more that are planet candidates right now that are waiting to be vetted. I talked about exoplanet diversity and why the composition is an important component of that, and how it's related to Earth likeness. I also mentioned that it's hard to measure directly right now, and that we can use these proxies like bulk density, but that those measurements even themselves are hard to make. And so that using the host star composition, because it's, we think, genetically linked in some way to exoplanet composition, we're able to hopefully learn something about the small planet composition. We're still trying to understand exactly what that relationship is, but the TESS mission will provide us with a much larger population of planets around nearby bright stars that we can really use to tease out what these relationships are. And then finally, I think Carnegie is really uniquely positioned to be able to make significant progress in the near future in understanding exoplanet diversity, both in terms of the radial velocity technique and the stellar abundances, as well as the experimental aspect that I talked about in the lab. And so with that, I'll end with another beautiful picture of Magellan by one of our staff members, Yuri Beletsky, and another quote from Contact, which if you've seen the movie, you'll remember that Ellie Arroway's father says to her, and then it repeats throughout the movie, which is, the universe is a pretty big place. It's bigger than anything anyone has ever dreamed of before. So if it's just us, it seems like an awful waste of space, right? And with that, I will take your questions.
Are there many ways to find an exoplanet if you're looking at the plane of rotation of that system head-on? Like, because if you're looking at it perpendicularly, the exoplanet won't ever pass in front of the star in your view. So are there ways to find it if that doesn't happen?
That's an excellent question.
Can you repeat the question?
Yeah, sure. So the question is are there ways to find exoplanets when you're sort of looking at them pull on so that the planet isn't passing in front of your line of sight? It's also hard to find exoplanets that way with the radial velocity technique because you're not seeing any motion of the star towards and away from you. And so right now, there's not a lot of good techniques for doing that. Direct imaging is one where you're actually just taking a picture of the system. But like I said earlier, that's really only working right now for young or very massive planets. And so there's certainly a bias in the planets that we're detecting because of this issue. But we hope and we think that there probably isn't something inherently different about those systems, just their inclination, and so that the planets that we're detecting are still representative of all of the planets, even the ones that we can't see.
I can't remember the axis, but you had one earlier chart where most of the materials were on essentially a linear scale, except for the nobles, is what it looked like. Why are those different, and do they mean anything?
Yeah, so, oh yes, sorry. So the question was, in the plot of the solar composition versus the chondritic composition, why there were noble elements, noble gases that weren't the same. And I'm not an expert in chondritic materials, but I think it has something to do with the different processes that those planetesimals experience when they're, after the star is formed and they're in the disk of gas and dust around the star.
Thank you for the lecture. Among astronomers, is there a consensus of how many stars they believe are in our galaxy?
So I Googled this today because the first quote that I shared said 400 billion, I think. And so I can go back to it real quick. I think, escape, here we go. I think that's about the right number. When I looked online today, it was more like 300 billion, so that's close.
Depends on how you define a star, too.
Yeah, of course, it does depend on how you define a star, yeah.
What's that? Yes.
Yeah.
Go ahead.
What evidence is there for rogue stars that you were talking about? If you're looking for the dimness of stars, then how do you look for a rogue planet?
Sure, so that's a great question. And there was actually a paper about this today or yesterday that came out. The search for rogue planets is mostly by looking for them, looking for light coming from planets that aren't around other stars. We can sometimes get an idea of where they might be. I guess that's the point of this paper, by looking for nearby systems that have a gas giant planet or multiple gas giant planets that would have ejected planets due to the movement of the gas giant planet in the system. But yeah, there's still a lot of research going on into how we would find rogue planets. We haven't really found a good example of one yet. Right now, there's some debate over whether things like brown dwarfs are technically rogue planets. It has to do with the definition of, or the understanding of how they formed.
Is there sort of, I know exoplanet research is fairly new, but in the future, is there something that's going to tell us that there's technology out there? I keep reading about new tests for this, new tests for which, it's kind of getting closer and closer to saying there's something that could be living on the planet, but is there something in the future that maybe could tell us that there may be technology on that planet?
Oh, I hope so. Right. All that you're right that we've been focusing on whether there could be life on other planets and the conditions for life. I think signs that there's technology or intelligent life would probably be something like a periodic signal that wasn't like coming from a star, but it was some sort of periodic light signal coming from a planet, or a known pattern, like a sequence of numbers or something. And actually, that's exactly what happened in the movie Contact. So that's where I'm getting my answer. But yeah, something that that is that wouldn't be naturally occurring in nature.
Brown dwarfs, do they emit infrared light or infrared pictures? Could you detect planets around a brown dwarf?
Right, so I should be repeating the questions, I'm sorry. The question is, could you detect a planet around a brown dwarf? Yes, absolutely, people are trying to do that. And there was a recent discovery, which you may have heard about, the TRAPPIST-1 system, the host star of that system is very, very cool. It's about the temperature of a brown dwarf. And so, again, this goes back to the definition of what is a brown dwarf exactly, how do those form? We're still trying to determine that. But yes, I think people are very actively searching for planets around brown dwarfs. It's hard because, like you alluded to, they're very cool, and so they're faint. And so they're even harder to find planets around than more massive stars.
To the extent that you have been able to determine composition of planets, have you found any that apparently have atmospheres?
So the question is, have we found any planets that have atmospheres? And the answer is absolutely yes. Many gas giant planets. There have been a few smaller super-Earth planets, so the size between Earth and Neptune, that we think do have atmospheres, that we've detected things like water in. But in terms of small Earth-like planets, there hasn't been a very good detection of an atmosphere. There have been some arguments for smaller planets based on their density and their bulk composition, that you couldn't make a fully solid planet of that radius and that mass. So there must be some envelope of more volatile material. But detecting the atmosphere of an Earth-like planet is still something we're trying to do.
Cindy, we have a question from
Oh,
the
yes.
live stream, I think.
Yeah, we have a question from our live stream, and it is, do you think there will be more small mass exoplanets detected using microlensing once WFIRST is launched, much like is expected with TESS with the transit?
Sure. So the question is, will there be many more small planets detected with the WFIRST microlensing mission? And so I didn't mention this, but microlensing is another technique that we use to find planets. It has to do with how light is bent around other stars due to their gravity. And so the WFIRST mission is predicted to find super-Earth and Mars-sized planets, but not Earth-sized planets. And they will likely be much farther away, and so also harder to follow up. So that's going to be a great mission for understanding sort of population statistics of planets, especially the longer period ones. But in terms of determining those planets' compositions, that will be challenging.
If someone happened to go rogue for some reason, would that affect the Earth very much?
Can you repeat the question, please?
If someone would go rogue, get kicked out of the galaxy.
Oh, if the sun? Is that what you're saying? Oh, if the sun went rogue, what would happen to the planets in our solar system? Well, so we do. We probably stick with the sun. But that takes me back to one of the first slides that I showed about how we learn about exoplanets and that environment aspect. If the sun goes into a different environment where there's different radiation, or where there's recently been a supernova, or there's other stars that are very close to it, that could absolutely disrupt the orbits of planets and certainly affect their atmospheres and perhaps, habitability on our planet. So I think the news is probably not good for that.
Now, when I guess it was Galileo discovered that Jupiter had 4 moons, well, looking at it for a long time, making careful philosophy, you only saw 2 or 3, and then you saw 4 and all that. Never saw more than 4. You're sort of doing the opposite of that when you're doing the transiting. You're not looking at it, but it's not from the planet when it is. Now, have you ever noticed a pattern of dimming and brightening that could result in multiple solutions for how many planets we're going around?
Sure. So the question is, when observing planets with a transiting technique, is there ever sort of degenerate solutions where it could be different configurations of planets? Does that?
It would look the same with 12 or 9 going around.
Right. Right. So would it look the same? Would the signature be the same with 12 planets or 9 planets? How would you distinguish that? Right. So, this is a huge source of confusion with the transiting surveys, and really means that we have to observe systems for a much longer period of time. Even something like the TRAPPIST-1 system, or any of the systems that have short period planets, there may very well be other planets in that system that we just haven't seen transit yet, or even that don't transit, that maybe are slightly outside of our line of sight. And so disentangling that, is really challenging. A lot of times people will try to use dynamical arguments, so that how many planets could you pack into a specific space around the star and still have them be stable for a long period of time, and thus likely still in existence for us to observe them. But it's very challenging. That's what that little multi-planet animation was supposed to convey.
Do you have any speculation on what's going on at Tabby's star?
So the question is, do I have any speculation about what's going on with Tabby's star? And this is a star that was observed by the Kepler mission and I believe also the K2 mission, which is the daughter of Kepler mission, its extension. And it has very weird light curves in that the dips, like we saw for the nice even and periodic ones for planets, Tabby's star they're not periodic, or sometimes they are, but sometimes they're not. They're all different depths, and it's varying on short time scales. What I think is probably happening is that there's some, material breaking up around that star, like an asteroid belt or material falling in towards the star that has varying levels of thickness or opacity. And that's just causing this hard to predict light curve. So I don't think people have said maybe it's an alien megastructure. That would be evidence for technology, but I still favor a more astrophysical interpretation.
Are there any exoplanets that orbit anything similar to our sun?
Yes, the question is, are there any exoplanets that orbit something similar to our sun? Absolutely. There are many planets that orbit stars that are similar in size and temperature to our sun. I don't know offhand whether those are more common than other types of stars, but we've detected many of those. The for lack of a better word, the holy grail, of course, is detecting an Earth-sized planet around a sun-like star. That's an Earth analog or an Earth twin. We haven't really gotten to that yet. We've detected many Earth-sized planets around smaller stars, but the larger planets around larger stars tend to not be in that Goldilocks zone where we think liquid water could exist on the surface. But it's still our goal. And with next generation telescope missions, not JWST, the James Webb Space Telescope, but something even beyond that, we'd be able to directly image those types of Earth twin systems and learn more about whether their atmospheres and compositions are really Earth-like.
Are there any exoplanets that are near black holes?
So all the exoplanets that we've detected, well, almost all the exoplanets that we've detected so far have been within our galaxy, and many of them looking away from the center of the galaxy, where we think that there's a black hole at the center of the Milky Way. So I don't know of any that are close enough to be in danger any more than our solar system is in danger. Great question. So Erica wanted to know, over time, will the understanding of exoplanets and exoplanet formation help us learn about galaxy formation and evolution? And I don't know if I have a good answer to that. I'm actually hoping that both of them we can study both of them together. I'm actually very interested in these extreme exoplanet systems that have compositions very different than stars around our sun. And so whether there are planets that were formed at the very beginning of the galaxy along with those first stars, or whether we can detect planets that actually are from other galaxies. I don't know that that's really so informative of galaxy formation. I guess in one aspect it is. It's learning about what planets form in the galaxy. So that's a question I'm very interested in.
Yeah, I'm going to ask you a question. I never do this.
Yeah.
The first time I've been 15 years I've asked a question. The record's going
I hope it's a good one.
So I'm just curious, what is your opinion on do you think we'll find evidence of life elsewhere in the next few decades?
So the question is, will we find evidence of life elsewhere in the next few decades? And I think 100%. I'm quite confident that we will do that. Whether that's a high probability of life on another planet, or whether that's life in our own solar system. As many of you may know, the Cassini mission is winding down, and as part of its final turns around Saturn, it observed some plumes coming off of one of the moons, Enceladus, and those plumes seem to have the right composition, and we think that the interior structure or the interior energy that's necessary to make those plumes coming off of the moon, all of that points towards that moon being able to host at least microbial life. And so I think it's a race who will win the life battle, whether it's solar system scientists or exoplanet scientists.
Excellent. All right, if there are any more questions